Hello, and welcome back to Math 112, Calculus 2. Today we have Lecture 19. Our topic of the day is trigonometric substitutions for evaluating integrals. The general methodology is to utilize the Pythagorean identities in order to integrate functions which are sums and differences of squares of numbers and variables. For example, we will use sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. 1 plus cotangent squared theta equals cosecant squared theta. Our first substitution would be x is equal to a sine theta when we're dealing with an integrand which contains a squared minus x squared. In this particular case, a squared minus x squared would equal a squared times the quantity 1 minus sine squared theta. And that gives us a squared cosine squared theta, which we're able to use to simplify the integral. In this case, dx is a cosine theta d theta. Now here is another possible substitution. Suppose we're dealing with an integrand which contains an a squared plus x squared. Then we let x equal a tangent of theta. In that case, a squared plus x squared becomes a squared times the quantity 1 plus tangent squared theta, which is a squared secant squared theta. dx is a secant squared theta d theta in this particular substitution. And here is the third possible substitution. X is equal to a secant theta for x squared minus a squared. X squared minus a squared becomes a squared times the quantity secant squared theta minus 1, which is just a squared tangent squared theta. dx is a secant theta tangent theta d theta. Now here is a specific example. We have the integral of dx over the square root of 9 minus x squared. If we let x equal 3 sine theta, dx is 3 cosine theta d theta. And we substitute in. We can simplify the integrand. And what we get is that I is just the integral of d theta. The 3's cancel, and the cosine theta cancels. So what I have is I is the integral of d theta, which is just theta plus c, a constant of integration. Solving for theta using our original substitution, we get that theta equals the inverse sine of x over 3. So the integral is inverse sine x over 3 plus a constant. Now here is another example. Suppose we wish to evaluate the integral of dx over the square root of 16 plus x squared. Clearly, a is 4, and we're going to let x equal 4 tangent of theta. dx is 4 secant squared theta d theta. We look at the representative triangle. If the tangent of theta is x over 4, the hypotenuse is a square root of 16 plus x squared. We substitute in. The 4's cancel, one of the secants cancels, and we get that the integral is the integral of secant of theta d theta. The integral of secant of theta d theta is the natural log of secant theta plus tangent theta plus a constant. The secant of theta can be readily obtained from the representative triangle. The secant of theta is the hypotenuse over the adjacent. And we have that there. And then the tangent of theta is just x over 4. So the final answer is the integral equals the natural log of the absolute value of the square root of 16 plus x squared plus x and absolute value plus a constant. Those 4's in the denominator can just be factored out and absorbed by the constant of integration. Now here is another example. The integral of dx over the square root of 16x squared minus 1. In this case, we let x equal secant theta over 4. dx is secant theta tangent theta d theta over 4. So we have that the integral equals 1/4 secant theta tangent theta d theta over the square root of secant squared theta minus 1. Square root of secant squared theta minus 1 is tangent of theta. So the integral becomes 1/4 times the integral of secant theta d theta. That gives us 1/4 natural log secant theta plus tangent of theta plus a constant of integration. Once again, we draw our representative triangle. In our representative triangle, the opposite side is the square root of 16x squared minus 1. The adjacent side is 1, and the hypotenuse is 4x. And in this way, we get that the secant of theta is 4x. This leads us to the final expression of our integral, 1/4 natural log of 4x plus the square root of 16x squared minus 1, close absolute value, plus a constant of integration. Okay, let's take a look at our final example, the integral of x squared dx over x squared plus 4. Now, from our previous lecture on partial fraction decomposition, we really could write this as 1 minus 4 over x squared plus 4. The integral of 1 is just x, and then it would be minus 2, the integral of arctangent x over 2, plus a constant. And we get the same answer using our trigonometric substitution. Here we let x equal 2 tangent of theta. dx is 2 secant squared theta d theta. The integral becomes 4 tangent squared theta times 2 secant squared theta d theta over 4 times 1 plus tangent squared theta. 1 plus tangent squared theta is secant squared theta, which cancels. The 4's cancel. And we're left with the integral of 2 tangent squared theta d theta. Tangent squared theta d theta can be written as secant squared minus 1 d theta. So our integral becomes 2 times the integral of secant squared, which is tangent of theta, minus the integral of 2 d theta, which is 2 theta, plus a constant. And our final answer agrees with the same answer we would have gotten using division. The integral is 2 times x over 2, which is just x, minus 2 arctangent x over 2 plus a constant. Hope you can join us next time.